Hi y'all. So on Wednesday I forgot to record the first few slides, so we'll just go through basically recursive definitions and then a little bit of structural induction here. So the big idea of structural induction, which is one of the key ideas this week, is that it's a way of proof that looks a lot like induction that you're used to, but it's on some sort of object that we've defined recursively. And so we can take advantage of that recursive structure. So in the induction that you've seen before, maybe you induct on some number, right? Some number n. And it's a natural number. You prove something for n, you look at n plus 1. Here, we're going to draw on a recursive structure instead, but that idea of sort of climbing the ladder still holds. So our recursive structure, right, this object, will have a basis step of its definition and then a way to generate the other elements of this set. And so our induction, for our base case, we can prove that the statement is true for the basis step of the recursive set's definition. And then in the inductive step, we can kind of assume the statement is true for the smaller pieces, and then use the recursive step of the definition and show that we get something that's still true. So let's do an example. So S is a set of ordered pairs of integers that's defined recursively. So here's how this recursive definition works. The pair 0, 0 is an element of S. And then for any pair AB that is an element of S, the pair A plus 2B plus 3 is also in S, and A plus 3B plus 2 is also in S. Right? So if I take AB to be 0, 0, since I know that's an element of the set, then the recursive step tells me that the pair 2, 3 is in S, and the pair 3, 2 is also in S. And from there I could keep building, right? If I took AB to be 2, 3, then I would get that 4, 6 was in S, and so is 5, 5. And then what we want to prove by structural induction here is that A plus B is divisible by 5. So we start with the basis step. So the basis element of our recursive set is 0, 0. So we consider 0, 0 for our induction basis step. A plus B here is 0 plus 0, which is 0, and that is indeed divisible by 5. And now we'll move on to the inductive step. We're going to assume that the statement is true for some pair A, B in S, and then check that it's still true if we apply the recursive step of our definition. So we'll check that our statement is still true for the pair A plus 2, B plus 3, and the pair A plus 3, B plus 2. So that's exactly what we do here. If we look at the sum of A plus 2 plus B plus 3, that's A plus B plus 5. Remember that we've assumed that A plus B is divisible by 5. So A plus B plus 5 must also be. And then we can do something similar for A plus 3, B plus 2. And so we've proven our statement, and that's how structural induction works.